So you're okay with recording, right?
Yes.
Okay, good. Just checking. So happy 2021, everybody. Hopefully it will get better than 2020. So today's speakers is Phil Barbeau. I'm not sure if I pronounce your last name correctly. But so he got his PhD at the University of Chicago working on coherent experiments, searching for coherent elastic neutrino nucleus scattering, light whip dark matter and axion, as well as Majorana neutrinoless double beta decay experiment. He then moved in a postdoc position at Stanford working on EXO 200. And after that, he joined Duke as an associate professor, working on both neutrinos and dark matter. So his group has developed a neutrino calibration facility at the Tunnel Tandem Van de Graaff facility that has been used to measure quenching factors in numerous neutrino and dark matter detectors. He is participating as well in the Legend 200 and Legend 1000 germanium-based neutrinoless double beta decay experiment, and he helped funded the coherent experiment, and today he will discuss the coherent elastic neutrino nucleus scattering. So I will leave you the floor. Thank you, Phil. Thank you very much. I'm very happy you are here.
Thank you. I'm happy to be here. Thank you for the invitation, Sylvia. You pronounced my last name however it's supposed to be pronounced. It's
okay, good.
So yeah, I came here to talk today about the COHERENT program, which is mainly coherent elastic neutrino nucleus scattering, which is a neutrino experiment at a facility in Oak Ridge National Lab in the US, which is called the Spallation neutron source. I'll tell you a little bit about it, tell you a little bit about why it's interesting, what we're doing, and then more broadly, what the community is doing, which is very exciting to see, and we're very hopeful for the broader CEvNS community. So what do we mean by CEvNS, or coherent elastic neutrino nucleus scattering? We pronounce it CEvNS. It's entirely possible to pronounce it CEvNS, but we like CEvNS better. So coherent elastic neutrino nucleus scattering has long been predicted. So about 46 years ago, it was predicted by two physicists, Dan Friedman and Fermilab, and then the ubiquitous Russian simultaneous announcement as well, where it was realized once the neutral current was measured and observed that there were potentially other collective phenomenon that might arise when neutrinos scattered off nuclei with this neutral current, this neutral boson. And that collective phenomenon gives rise to a cross-section that is proportional to the weak charge of a nucleus squared. And so the number of neutrons in the nucleus squared. Since it's collective phenomenon, it's this very quantum mechanical effect. So it can only happen if the initial and final states of that nucleus are basically identical. You can't excite the nucleus. There are collective phenomenon with nucleus excitations that give rise to larger cross sections, but the largest cross section, the one that's completely proportional to n squared, is one where all of the nucleons recoil in phase together. And what that means is that you end up with a very high cross section, the highest cross section at these very low energies, but a very low energy nuclear recoil because of very low momentum transfer. The de Broglie wavelength of this momentum transfer is very low. And observing, and no other particular signature, just a very low energy nuclear recoil. So why is it interesting? From a theoretical perspective, CEvNS is extremely well predicted. There's very little uncertainty. There's very little nuclear uncertainty, especially for the lowest energy recoils, which you might expect for most other neutrino nuclear interactions where there can be 300% uncertainty in a prediction. The uncertainty in the standard model prediction for this is at the level of less than 0.5%. So one of the highest precision cross sections that you could potentially measure. And that means that there's a lot of physics you can do with it, especially if you're looking for deviations from the standard model. One of the first things, though, before we get to the precision aspect of things, is one of the first things that was realized was that this real high cross section for neutrinos could actually be an answer to a big open question at the time, which was why in fact, how do you actually get supernova shocks to explode? It was very difficult in some of the earlier models to get supernova shocks to actually explode. They tended to collapse back on themselves. And this really high cross section with all on nuclei with all of the neutrinos that were leaving a nucleus could reinvigorate a shock and potentially explain why supernovas actually happen. That's not the only astrophysical reason why this is interesting. So the neutrons themselves in the nuclei are the weak charge of that nucleus. And there is a neutron skin depth in a nucleus. The neutrons themselves are pushed out past the core of the proton radius. As you lose coherence with smaller and smaller momentum transfer, so higher energy recoils, so you get less and less proportional to the square of the number of neutrons, what you're actually testing is the neutron distribution in that nucleus. And so if you can use coherent scattering to measure that neutron distribution, you can actually measure the neutron skin depth, or how much the neutrons are pushed out past the protons. And that has a direct correlation to the neutron skin depth and the equation of state and the stiffness of neutron stars. And so it's a very interesting measurement you can perform here with neutrinos on nuclei without relying on any other models of the nucleus or lepton-nucleon interactions to try and understand why neutron stars behave the way they do. So that's one interesting reason. But we're going to go through a panoply of them, and there'll be many things to talk about and many things I've left out. Another interesting thing, these are neutral currents. You're only going to observe a neutral current with this particular interaction because you have to have the initial and final state be the same. And that means you're particularly sensitive to other additional neutral currents in the standard model that would also give rise to a coherent phenomenon and change the prediction of the cross section, move it away from what is assumed in the standard model beyond that sort of 0.5% uncertainty that is currently in there. So it's proportional to the weak square of the weak charge. And if you have some new Z prime, a Z star, or Technicolor, or any other type of a light neutral, a light Z or a heavy Z, they show up in different ways in the theory, and some of them have kinetic mixing. But generally speaking, what they're going to do is add or interfere with the cross section. And so some difference will actually allow you to measure it. And we do. We try to put constraints on it. But one of the ways it shows up, aside from looking for things like non-standard neutrino interactions or extra Z's, is as a change in what's known in the weak mixing angle. And so you can constrain the weak mixing angle with these measurements. It's important to point out that current generation experiments aren't doing a lot in this regime, although they are operating at a low energy. They are having a sort of second order effect on reducing some of the theory uncertainties that go into atomic parity violation and atomic clock type measurements. And so they are, at the moment, they're having a small effect, but we expect in the future them to have a more interesting effect on weak mixing angle. With new Z's come new types of interactions for neutrinos. So broadly speaking, what we try to do when we try to lump together in the CEvNS community and now more broadly in some of the other neutrino nucleus scattering interaction communities, sort of all beyond the standard model processes that would change the way in which neutrinos scatter off protons and nucleons or the gluon components, the quark components. We lump them into sort of non-standard neutrino interactions. So if you are more, if you're more interested, if the neutrino develops more of a cross section with protons or more with neutrons or with the up quark or the down quark, or that's going to be a non-standard neutrino interaction. And so we can actually constrain these, especially if we can actually change the number of neutrons and protons in a nucleus, and sort of play with it for several different nuclei and look at sort of how the cross section behaves over several nuclei. We can actually really constrain any new non-standard neutrino interactions, new neutral weak currents, or anything axial currents that might interact with nucleons differently. And so that's something we'll do, and you'll see plots later in the talk where we have two axes, where we've sort of broken down all of the possible theories that you could, all the extra parameters you could add to these theories. Into an effective parameter that might modify the electron neutrino interaction for the vector interaction with the d quark versus with an up quark. And so that's, I mean, there's a lot of things that are marginalized there, but that's the most common way you'll see it. And you'll see these interactions that can be of order unity, at least up until when they can still be of order unity. And they're sort of put in this two-dimensional plot here, and they have this diagonal characteristic of their potential interactions. Of course, because it's a neutral current process, and it's a very well predicted standard model process, it can be it can be a very interesting player in searches for sterile neutrinos. So one of the most interesting ways in which it can play a role in searches for sterile neutrinos, it would be via total neutral current disappearance. Of course, we know that experimental searches, say for instance at reactors with inverse beta decay, are only going to be able to look for electron neutrino disappearance and potentially reappearance, depending on the baseline. And one of the things, regardless of whether it's at a reactor or, for instance, at a spallation source, one of the things you could do with a coherent scattering detector, potentially with more than one detector, is to do a total neutral current disappearance measurement in the sterile neutrino field. You're going to need still large detectors, even though the cross-section is very large, in order to compete with the current generation of, say, inverse beta decay experiments and long baseline experiments, but they can play an important role. And this has been long predicted for now actually almost 40 years, 35 years ago. Of course, we all know, for anyone who's studying dark matter, that eventually the current generation and certainly the next generation of dark matter experiments are going to become sensitive to this particular background of seeing nuclear recoils that are indistinguishable from WIMPs, at least with the current generation of technologies, that are due to neutrinos from solar neutrinos and from atmospheric and diffuse supernovas and extragalactic supernova, neutrinos. And so this was long pointed out ago by Druke and Studosky, and then really put into context by Julian Biard and Tali and Louis Strigari. And now this is a really important thing. And only just recently have we seen the first limits for such a measurement from the Xenon 1-ton experiment, which was very exciting to see for the field. So it's an important background. It's important to understand the cross-section well, to know that that's what the cross-section actually is, and to understand the detector response for all of these experiments at these low energies, if you want to subtract this background. So CEvNS is a very broad, has a lot of things you can do with CEvNS. Of course, this is a nice illustration of sort of the new sort of types of experiments that now can be done now that we've measured CEvNS and now that many experiments are coming on to measure them. Of course, we can study the neutron distribution in the nucleus and look for sterile neutrinos. We can do solar neutrino experiments, although we're going to need larger scale experiments to really do that. Search for supernovas, of course. Dark matter, there's a lot of dark matter experiments that you can do at these neutrino facilities using CEvNS detectors, looking at new interactions, and also applications. There are potential interesting applications for reactor monitoring that might prove useful. And because of that, CEvNS is a very popular thing nowadays. So the coherent experiment is on here, and that's the experiment I represent primarily. But we have a pretty broad community of people that have now developed concrete plans to build experiments to search for coherent neutrino scattering. And it's a community that actually is really congenial and comes together really well, helps each other out. We all work very close to each other. Many of us are on multiple collaborations. We calibrate each other's detectors. We try to find each other's sites for working for the most part. And we're all very excited about the kind of physics that can be done. And the reason is because we've been waiting for decades to get this done, and we're all very excited to see where things can go. So where do we think things can go? So this is a little bit of a preview, and then I'm going to stop talking about the community until the very end. But over the next 10 years, or the next couple of years, actually, I should say, next 3 years, we expect a lot of experiments to come online. And the two primary ones are going to be experiments at spallation sources, so stopped pion facilities like the coherent experiment, which I represent. Of course, we observed coherent neutrino scattering 3 years ago, and I'll talk about that. And we're continuing to do so in different isotopes and attempting to improve things. There are other experiments that are attempting to go to spallation sources at both at the Lujan Center at Los Alamos National Lab and ESS. And there are upgrades for these facilities as well. But on top of that, there's a lot of experiments that are trying to go to take detectors to build lower threshold detectors, to look for really low energy recoils, and take them to nuclear reactors for a variety of reasons. These two approaches are very complementary to each other in terms of the physics, and then there's the added interest in applications. So this is just the next 3 years. But really, there's a plan. There's really concrete plans to go out for the next decade, and beyond that, it's really hard to predict where things are going to go. So you can sort of see many upgrades in terms of what experiments are planning and what they hope to do, what the facilities are planning to do, what kind of reactor deployments we can expect, and upgrades beyond that. But on top of that, I've included here on the bottom 2 new categories of searches that we expect to start actually playing a real important role in the field, which are the observation of neutrinos from boron-8 solar neutrinos. We're going to see, we think, 4 experiments to be playing a role in that in the very near future. And then, of course, the ones from atmospheric neutrinos. So that would be something like Darwin, or potentially, if there is a supernova in the galaxy, we have very large experiments that would be able to be sensitive to the neutrinos interacting via coherent scattering in their detectors, starting very soon and then carrying on into the next decade. So there's a lot to be said about coherent neutrino scattering. There's a lot of experiments coming on it. So there's a lot of knowledge transfer in the community right now that makes it very vibrant and very fun. Okay, so I'm gonna pause the community chat there for a second and just tell you about coherent. So coherent, the provenance of coherent was that we used to be many different researchers, each of us trying to build our own coherent neutrino scattering detector on our own, and all of us being subcritical in terms of the effort and the resources. And we all finally came together with Kate Schulberg and Yuri Efremenko at Oak Ridge National Lab at the Spallation neutron source, and in a coherent way, decided to combine our efforts and just try to observe coherent neutrino scattering finally, like actually get it done. And so what is the Spallation neutron source? Well, it is a pion decay at rest source. So it's there's a proton beam that produces pions. These pions themselves are now stopped in a liquid mercury target that takes up most of the heat, where they decay. And for the most part, they're going to decay into mu pluses. They give off that initial prompt decay into a mu plus will give off a muon neutrino. That muon neutrino has an energy spectrum of about 29.9 MeV. So that's a pretty sizable energy, but not so high in energy that you lose coherence. And it's and it follows the timing characteristic of that neutrino pulse, the proton pulse, which comes in at 60 hertz and lasts with a full width of about 350 nanoseconds. So a nice background suppression there from that prompt pulse. Then the muon decays, of course, with a characteristic lifetime of 2.2 microseconds. You get more neutrinos out of that, and so you get a tail of some nice neutrinos in the delayed neutrino. So you have a prompt neutrino delayed that happens 60 times a second, and you have nice gaps in between in which to measure your background and reject things. And so it's very nice. It's a facility designed to stop pions, so you can actually get a really high flux of neutrinos here. We've unfortunately, the Spallation neutron source is also a facility designed to produce neutrons, and neutrons, of course, produce nuclear recoils that look a lot like coherent neutrino scattering. So it took quite a bit of effort to find a location in the facility that was neutron quiet. And so we finally did, thanks to initial efforts from Fermilab, Indiana University with their CIBAF detector, and with the neutron scatter camera from Sandia National Lab, all members of the collaboration, where we, and of course, members of Oak Ridge National Laboratory as well, who found a basement alley, which was at its closest about 20 meters from the target of where the neutrinos are being produced. That runs along the length of the proton beam, and it has about 6 meters water equivalent overburden and a bunch of backfill, about 20 meters of concrete and rock backfill in between there that shields these neutrons that are coming there. So it's a very neutron quiet location. And we've deployed a number of detectors in that back alley. Of course, we're restricted because this back alley is an egress point for safety issues. So it's only about 6-7 feet wide. And we need 3 feet wide in order for everyone to escape. So if the challenge is, of course, we have to build detectors that are neutrino experiments, but they're only 3 feet wide. And so we build many of these along the alley, but that's the real difficulty there. And our initial goal here, one of our initial goals, not the ultimate goal, but one of them that we really wanted to see was a demonstration of coherent neutrino scattering across multiple nuclei that showed the n-squared nature of this cross-section. Of course, this is something of a holdover, a little bit of residual effect due to the fact that we were a collaboration made up of many people who each had our own favorite detector that we wanted to build. And it turns out that we're being relatively successful in deploying each one of these and getting them all built and deployed and measured. And that's really exciting because each one of them brings a different strength and a lever arm on the kind of physics you can reach. So how many detectors have we built and how much sort of exposure have we gotten? We've gotten quite a bit of exposure. Since late 2013, we've seen something like close to 9 times 10 to the 23 protons on target. So that is that is more than a mole of protons on target. Many of our detectors have actually been deployed and operating and observed neutrinos during that time. Some of the ones that you see up here are just measuring neutrons, backgrounds. Some of them are measuring neutrinos for coherent scattering. Some of them are measuring neutrino interactions that are more inelastic, that might be of interest as a background to CEvNS or are interesting because of nuclear astrophysics, because of their role in, say, post-processing in the neutrino wind after a supernova, that sort of thing. Our process nucleosynthesis, that sort of thing. So there's a real interesting physics that we can do with this facility. Okay, so that was a lot of detectors about. I'm not going to be able to tell you all of them, but the one I'll start with is the cesium iodide program. That was the first neutrino detector that was deployed. And so 3 years ago, well, more than 3 years ago, we deployed it. 3 years ago, we reported on the first observation of coherent neutrino scattering ever. And that made the cover of Science. Unfortunately, that cover of Science has a detector that wasn't the detector that did the work. And in fact, it's actually much smaller than the detector, not much, in fact, a few smaller than the detector that did the work. But it's a neat picture, so Science liked it. And the point here is that we saw both the expected recoil distribution from CEvNS and the timing structure that we expected from the beam, which convinced us that in fact we were seeing it. We saw that signature at about almost 7 sigma. We rejected the null hypothesis. The observation agreed with the standard model within 1 sigma. Now there were large statistical uncertainties and some systematic uncertainties on event selection, but the largest uncertainties actually came from the predicted rate that we expected to see, both from not really knowing the neutrino flux and the sort of uncertainty of the neutron distribution in the nucleus, because at the Spallation neutron source, we do begin to see a very small effect due to the loss of coherence that I talked about. But the biggest one was, since these detectors are operating very near threshold, and we're really at the bleeding edge of a lot of the technologies that we're using, we really have to understand the energy calibrations at those thresholds exquisitely well in order to predict the CEvNS rate well. And so at the time, we knew this, but we took a very conservative approach to our understanding of that calibration, that quenching factor. And that was the largest uncertainty at the time. And that's what you see dominating that gray band on the expected number of counts from CEvNS. Something I want to point out that we really liked and that we are continuing to do is that we're releasing all of the data so that it's publicly accessible, so that people, phenomenologists and other experimentalists can study it and analyze their own data with their own favorite theory, or in case they think we did something wrong, which is entirely possible. And in fact, there were several things we did wrong with this first release, that some of which we discovered ourselves and some of which phenomenologists and theorists reached out to us very tentatively and said, excuse me, did you notice this one thing in the data? And we said, No, we didn't. Thank you for pointing it out. So there were a number of things that we thought was that came out very, very positively after a result of analyzing, releasing this data set, and has really improved the analysis as a result. And we have a very cooperative relationship with the phenomenologists in the field, which we really appreciate. So we're continuing to do this with new data sets, and we're extending it to anything that we produced, any calibration or analysis or neutrino measurement. It seems like we have enough manpower and resources to maintain the practice of releasing all of our data sets in an accessible way so that the community can see them. But of course, manpower is always the issue on that. So it can be a challenge, but we think we're going to be able to do it. So let me talk briefly about the quenching factor, since that was the largest uncertainty from the previous, that first measurement on cesium iodide. So this can be challenging to measure with new detector technologies. What we do to measure it is generally speaking, we produce neutron beams, clean and as systematically controlled as possible, and we try to scatter them off of the detectors of interest into specific kinematically constrained conditions, angles, and measure these neutrons that scatter out, and then simultaneously measure the response of the detector, because you'll have a recoiling nucleus with a very specific energy when you do that. So we did that at the time. The picture you see here isn't cesium iodide. That's actually the super CDMS collaboration brought a cryogenic silicon detector that was working in a high voltage mode to try and calibrate their low energy thresholds. We've calibrated their detector with the same facility. And that one was interesting. We used a large dewar of liquid helium every night for several weeks. It was quite an experiment. But the facility itself that we generated, which is neutrons that are tunable, monoenergetic, collimated, and pulsed, gives a very tight constraints on what we can do with measuring these detector responses. Unfortunately, at the time, we had produced two measurements within the collaboration that disagreed with each other. And so we took a very conservative approach here. You can see here the conservative gray band that we took was our uncertainty in the quenching factor. Because we really didn't understand the difference between the blue and the red dots that were our own internal measurements. And since then, the facility has been used for many collaborations and many experiments within and outside of Coherent. So let me just say that we've performed now a total of 5 measurements. Well, there's 5 here that you'll see on this data set. There's a 6th measurement that hasn't been analyzed yet because it's very fresh, to readdress this quenching factor uncertainty, this discrepancy. And we think we've identified it. And it has to do with a series of analysis, very subtle analysis effects in how you treat the waveform and how you calibrate what a single photoelectron is and the amplitude of those single photoelectrons. But there will be a paper on detailing this in great detail coming out. The long and the short of it is, it was a very confusing episode for us. We've even calibrated the phototubes used. The linearity of the calibrations have been demonstrated over a very large dynamic range using the same facility that DarkSide used with their collaborators in Russia, and have continued to use the same photomultipliers throughout the process, the same photomultiplier, I should say. And we've resolved what we think are these discrepancies, and now have a much tighter uncertainty on the quenching factor, on the error band. So that's great. This uncertainty now goes down to contributes to less than 4% of the uncertainty from the quenching factor. And so just a little while ago, earlier this year, maybe a month and a half ago, but we first announced it at the Magnificent Sevens conference in must have been November. We have new results with more data, a better quenching factor, and better analyses of some of the subtleties in the waveforms of the cesium iodide neutrino runs. And we now have a much better measurement of coherent scattering on the cesium iodide crystals. What you see here are the results of 2-dimensional likelihood fits to the amplitude of the signal, the number of photoelectrons that were observed. The roll-off at low photoelectrons around 10. That is due to threshold effects that come into play because of various cuts. And on the right plot, you see the arrival time in microseconds after the beam pulse. Of course, steady state backgrounds are measured out of time. And there are other potential backgrounds from neutrons that are produced that we have constrained to be less than 7%. And we see this, so this measurement is now far superior with much lower uncertainty. The largest uncertainty, which was the quenching factor, these are the green bars that you see there. The new quenching factor uncertainty in magenta is much lower. Our statistical uncertainties are lower, of course. Other uncertainties are slightly lower or have remained the same. And the next dominant uncertainty that we have to deal with is this uncertainty from not really understanding what the neutrino flux is. What is the amount of neutrinos produced from a stopped pion decay from that proton pulse? That physics is not really well constrained better than 10%, and this is something the collaboration will be addressing soon. So the cesium iodide result that we show here is now far superior. We reject, we prove that CEvNS exists at something like 20 some sigma. That's not really the game we're playing anymore. What we're really trying to do is test the standard model. So our error bars, our uncertainty on the cross section are much reduced, and our uncertainty on the predicted interaction are also much reduced. And so we're doing far better in terms of testing new physics. That measurement, that data point that we see here is now put on the right-hand plot with much reduced error bars. Just for the moment, I want to highlight something, which is the black curve is the standard model prediction when you don't account for the loss of coherence due to the neutron distribution in the nucleus, and the green band are sort of a family of curves sort of illustrating the uncertainty in that the effect of that loss of coherence due to the neutron distribution in the nucleus. So we're clearly observing it here. It's not fundamentally a problem for experiments with lower energy neutrinos, such as those at reactors. So, okay, that's cesium iodide. You'll see another data point on there down at Argon. We've, in the meantime, also performed a measurement with a liquid argon detector, and I'm going to tell you about that next. So very briefly here, I'll tell you about the liquid argon program. It's an exciting program because it was an relatively easy thing for us to start, because we were able to use an existing liquid argon detector provided to us by Fermilab, and it was upgraded by Indiana University to really improve the light yield to a point at which it's not state of the art, but it's certainly not anything to shake a stick at. Which is about 4.5 photons per keV light yield, or I should say photoelectrons per keV light yield. So the interesting thing here is it's a much lower N, but it's also an even nucleus. And so we consider it a really interesting candidate for a much larger scale detector, something at the 10-ton scale and also potentially at the 20-ton scale. So it's the beginning of a potentially very interesting program. So what did we observe? So the thing is, you're going to have higher energy nuclear recoils, but you still have to understand that quenching factor. And so, unfortunately, we have not been able to measure that quenching factor, the detector response to nuclear recoils. But because of the very mature programs in the dark matter community, there have been two very high quality recent measurements of the quenching factor in liquid argon. The scene measurements and the ARIS measurements, in addition to some previous ones, which had a lot larger scatter and a lot larger uncertainty error bars, that have really done a good job of nailing down that quenching factor for the community. We still intended to add to that ourselves, but we've been very lucky that the community in the liquid argon quenching factor program has managed to produce these measurements and really helped that result. Okay, so what was the result of the liquid argon program? Well, I'm not going to go into a ton of detail. I could go into great detail about PSD and backgrounds and beam-related neutrons, but that's another talk, and I'm really running out of time, and I have 1,000 things I want to tell you. So I'll just say that what we've been able to measure is this cross-section on liquid argon, and it agrees with what we predict within errors. It's coming in a little high, but like I said, it's completely reasonable within errors, and there's the largest uncertainties come from a combination of beam-related neutrons and statistics, and of course the beam flux uncertainty. So what can you do with this? Well, I talked to you a little bit about non-standard neutrino interactions. The first plot up here on the left, that's the first plot, the constraints we were able to make, the first real constraints on non-standard neutrino interactions for heavy mediators since the CHARM experiment. So the CHARM experiment is shown in gray. Our first results from cesium iodide were shown in that sort of purplish blue band. Now, just recently, we had our liquid argon results paper published in in PRL, so that's not preliminary anymore, but the liquid argon experiment was able to improve on those results. And that's what you see in the next two plots to the right of that, which show a much tighter constrained parameter space. So for those of you wondering why there are two bands, this has to do with the way in which these epsilon parameters arise in the n squared nature of the cross section. And so that square gives rise to both a positive and negative term, and you can get a splitting or degeneracy there. The interesting thing you'll notice is on the rightmost plot is that the cesium iodide and the liquid argon constrained regions have different slopes, and that's because of the different ratios of numbers of up and down quarks in the nuclei. And so that's the game you can play to really try and reduce, in addition to increasing the precision, you can change the target nuclei and really try to reduce the parameter space to look for anything new that shouldn't be there in a standard model. Our most recent result from cesium iodide is now on the bottom left, and you see that's even significant more improvement over the liquid argon results. And so we're working on a combined analysis too on that, which should begin to show some really interesting work. I should add that there's a recent paper from Xenon 1 ton out that actually also makes plots in this parameter space, and this is a wonderful thing for the field to actually begin searching for these things. Some interesting other plots that you can make from these cesium iodide results. Two that I particularly like the most. On the rightmost plot, you can look at the potential for a non-standard neutrino interaction to give rise to an oscillation in oscillations parameter, a large mixing angle dark solution, which is a potential degeneracy that arises that prior to the CEvNS experiments was left unconstrained and could have caused a real problem for the future of the Dune experiment. But as you can see now, we're actually doing a pretty good job of constraining that phase space and showing that dark solution is not true. And that was a really neat result that came out as a result of a phenomenologist actually analyzing our data. And the leftmost plot, one that I particularly like, is because we're able to study the timing nature of these neutrinos, the prompt muon neutrinos and the delayed neutrinos, which are a combination of anti-muon neutrinos and electron neutrinos, we're able to sort of measure in a degenerate way the different cross sections between these two electron neutrinos and muon neutrinos on the nuclei. And there are some interesting things that can arise there, ultimately including potential effects due to the effective neutrino charge radius and how that might change with neutrino flavor. Okay, so what do we have coming up next? We have a lot of detectors in that hallway, and we keep putting more. And now we actually have a whole committee just to argue about space. But I think everything's going fine. But the detector I want to talk about right now is the one we call the heavy water detector, the D2O detector, which should be familiar for any veterans of the heavy water experiment in Snow Lab. That's not what it actually looks like. This is the version of the experiment that has gotten preliminary funding from the Department of Energy in the US. The heavy water has been amazingly, if you're part of a weapons lab in the US, it turns out people want to get rid of their heavy water and give it to you for safekeeping. And so Oak Ridge has managed to obtain more than a ton of heavy water that we can use to try to look for neutrinos. In particular, what we're looking for is a charge current interaction on deuterium. And the reason is because that cross-section is understood theoretically at the level of 2 to 3%. And some people, depending on who you talk to, think they can get it down to 1.5%. But 2 to 3% works for us right now because we're sitting at 10% uncertainty. And so we're intending to look at the Cherenkov light from a charge current interaction in this heavy water to normalize the cross-section or normalize the rate of neutrinos that are actually coming out of the facility. And we need to do it now because the facility is going to be upgraded. And we hope to be able to measure this neutrino flux and then apply it backwards to experiments that have already happened. But after the upgrade, we may not be able to do that. In addition to measuring that interaction, which you can see here in the turquoise color, we'll also be able to get the first charge current measurement on oxygen-16 as well, we hope. And so that's another sort of ancillary physics program that we can pull out of this. There are a lot of such programs in Coherent where we have such a high neutrino flux, you can put almost anything in the hallway and measure the neutrino interaction on it if you're interested and you have the detectors to do it. Okay, so the next thing after normalizing that flux is to deploy a new nucleus to look for coherent scattering. One that is already underway and was funded by the NSF was to deploy 16 kilograms of germanium, high purity germanium detectors. These are the same detectors that are used in the planned Legend 200 and Legend 1000 experiments. They're inverted coax p-type point contact detectors. The party line is that they have thresholds, masses of about 2 kilograms and thresholds of less than 150 electron volts, or that noise, I should say. But in actuality, we're finding that the masses are coming in to be about 2.2 kilograms and noise about half of that. So it's really quite exciting. They're really amazing detectors. 5 of them have already been delivered, and basically we're nearly finished with our order, and the deployment is being planned imminently. Hopefully in the first half of this year. Well, certainly in the first half, hopefully in the spring of this year, assuming COVID is okay. So what do we expect to see with germanium detectors? Well, these are much lower threshold detectors, but they're still large mass. And that means that we'll have much fewer problems understanding the threshold effects, because the threshold is essentially going to be effectively zero here. We're going to have a threshold that's, in terms of electron equivalent energies, that's well below a keV. So we won't have any uncertainties in terms of if a recoil is above threshold. And that means that if we can really measure our quenching factor well, we're going to be able to measure the shape of this recoil spectrum really well. And that's really important for searches for non-standard interactions and for trying to understand the neutron distribution in the nucleus, because those things affect the shape of this recoil spectrum. So it's quite exciting. And because these detectors are much lower background than any of the other experiments that we've deployed, then we expect a much cleaner signal, and so we're really excited about what's to come. Okay, so that's it for the CEvNS detectors. Well, not quite. There's more, but there's a lot of other detectors I want to tell you about that we're dealing with. The first one is that we are planning a ton-scale liquid argon experiment. Ultimately, we hope to get to a 10-ton scale and potentially with 2 experiments, but we have to build a ton scale. We think we can build a ton scale experiment in the hallway. And one of the real interests, aside from real precision measurements for CEvNS on Argon, is that it's a large enough experiment to begin doing neutrino charge current measurements on Argon itself, with neutrinos that have approximately the same energy or the same type of energies that you would expect to see from supernova. And that's really important for the DUNE science program. If the low energy part of the DUNE science program is going to see neutrinos from supernova, it needs to know what the cross sections are and what the signatures are for the various channels. And this is something we can do to calibrate those all out. We expect to be able to see that neutral current and charge current interactions on Argon in such a detector, so long as we can get the dynamic range right. That's the real challenge. You need to be able to see coherent scattering with really low keV scale recoils and charge current interactions with tens to almost 100 to 50 MeV electron interactions. So it's a really large dynamic range to be able to do simultaneously, and that's the challenge. The other challenge is actually deploying such a mass in such a large space. But if you manage to do it, coming back to this plot of the cross section of the electron cross section, neutrino cross section versus the muon neutrino cross section, we can begin to sort of project our future sensitivities for what things are going to look like. Now, cesium iodide is a program that has been shut down, so it's not going to continue. And so that sensitivity, the big curve, is basically static, but we expect to really improve it with liquid argon, with a ton scale liquid argon, and with a few, with about 10 kilograms, 16 kilograms of germanium. Now, there's something that's not on here that I have mentioned briefly, which is the sodium iodide program and the search for sodium recoils, because this is something we also want to look for. But the reason it's really not on here is because of 2 reasons. One, we expect that the first set of measurements with sodium iodide detectors is going to be suffer from the backgrounds that we see in the detector, so there'll be higher background. But also the theoretical prediction on sodium, because it's not an even nucleus, and because it's so light that it's not dominated by coherent scattering, there's a lot more uncertainty than what I claimed earlier. And so it's a lot less interesting to put on a plot like this, where you might be looking for effective neutrino charge radii. Okay, so what have we done with sodium iodide? Well, we've deployed a prototype detector of 185 kilograms. It's an arrayed detector, in order to look for a very high energy signal, the charge current interaction on iodine 127. This was an undergraduate thesis project, if you'll believe it. And it was deployed and has been running now, and is I think the most recent projections are that we're well above 5 sigma, so probably 5.7 sigma, and we expect to unbox soon. And so we'll be able to get the first measurement of this process since the LSND experiment, which measured it, the sort of exclusive cross-section in a completely different way. And we'll be able to measure the sort of inclusive and exclusive cross-section of this. We think we'll be able to differentiate them. And it's interesting because this can have an effect. It's highly affected at the level of about 30%, which is the current measurement uncertainty, to the quenching of the G sub A in this process. And so we think we can help constrain G sub A quenching in this particular nuclei, which, given the potential to calculate some ab initio models for this interaction, might actually help some of the nuclear theorists get a handle on neutrino nuclear interactions. The array ultimately is going to be upgraded to be about a 3-ton array. There's one of the modules that you see right there that will be stacked together. So we get much higher statistics. So we're going to get really precision measurements of the charge current interaction on iodine 127. We also think we might be able to get charge current measurements on sodium. And we expect to see some charge current measurements on other targets that are nearby, say from iron, that sort of thing. But we also hope to simultaneously, either in parallel or in series, depending on the funding available, to double the electronics. We have the electronics the DAC to do in series now, which is to look at the coherent scattering on sodium. And the interest there is that it's got a very large axial current contribution. And by very large, I mean of the order of 5% for the highest energy recoils. So we might actually be able to start getting a handle on the magnitude of the axial currents using this. Okay, that's not the only charge current measurements we have. We also have a couple experiments we call neutrino cubes that are measuring charge current interactions on 2 nuclei right now. One is lead, which is of interest in our process nucleosynthesis. So if you have lead being produced in, say, kilonova or in supernova, and you have a very large neutrino wind, one of the things that can happen is that the neutrinos can spallate or produce more neutrons when they interact with them, and a more neutron-rich environment will give rise to the ARB process. And so it's depending on what that cross-section is, it's potentially very interesting for nuclear astrophysics. It's also potentially a background for us because our detectors are shielded by lead. So if a neutrino is going to come in that's pulsed, interact with lead, produce a neutron, and that neutron can then get to our detector, we need to know what that cross-section is, attempt to shield it, which we generally do, and knock it down with water or polyethylene shielding, and then try to understand, include it in our model. The other one is iron. So iron we do, one, because there's also a lot of iron in our shielding. The cross-section for neutron production is much lower. In general, the charge current cross-section is much lower. And we expect to have potentially interesting results there in the near future as well. But we expect these results this year. I think to say we're nearing data unboxing is really being disingenuous. I don't know that there's much left for us to do before we unbox, but except we had a Christmas break, so that's that. So that's some of the interesting physics we're doing, and it's not the least of it. There's an interesting program we're doing right now to look at neutrino-induced fission on thorium. We're trying to see if we can actually deploy such an experiment. We have all the spare parts, and we're just trying to make sure that we can actually disentangle spontaneous fission in thorium from a fission in thorium that might be produced by neutrino. And the reason is because why not? It might actually be able to fit inside one of these neutrino cubes. And we have the thorium, for which is crazy to think about, but we have it. So this is the beginning of the end. So I want to tell you about some of our postdocs. We have a very rich program and lots of responsibility for our postdocs and graduate students. We've had 2 PhD theses that have resulted in awards at the APS level, and really a whole cadre of really excellent graduate students and postdocs that are becoming experts in a broad range of technologies and in this burgeoning field of CEvNS, which is very exciting. So this new field is really just beginning. I mean, Coherent is trying to get a bunch of measurements out there, but we're also trying to encourage as many people to participate in this field as possible, and helping people with reactor experiments or other spallation source targets, other detector development. We certainly benefit greatly from the work that's done in detector development and background reduction in the dark matter community. And so there's a very rich set of physics to be addressed, and really we all as a community need to work together to address that physics. We can expect a whole bunch of really interesting reactor experiments turning on soon. Connie, which has already produced some very preliminary constraints. CONUS also has produced constraints with germanium detectors at a reactor in Brokdorf. The MINER experiment, which is a spin-off and related to the super CDMS technology. The RED experiment, which is a Russian liquid xenon two-phase experiment. The Ricochet, which is a bolometric experiment. Nucleus, which is also a bolometric experiment. They're really trying to reduce thresholds to the point. Some of these experiments are trying to reduce thresholds down to tens of electron volts, which are potentially very interesting in terms of monitoring nuclear reactors. So there's a great deal of physics that can be measured. So I want to kind of come to this plot here and give you some time to look at it. If you plot the neutrino, if you were to 5 years ago, if you were to tell me that we would have, you know, 2 nuclei with CEvNS measured and 3 other nuclei with constraints on those cross sections, I would have been stunned. But really, in the last 3 years, we've gone from no measurements of coherent neutrino scattering to what is that, 5 now. Some of them have seen it, and some of them have just put limits on it. So this plot shows the flux average cross section in green for experiments that might happen at the Spallation neutron source, stop pion beams, with solar neutrinos, boron-8 neutrinos, and that's what you see in magenta, and then at reactor experiments in red. And so you can see that the xenon experiment has put a constraint on the cross section. Depending on how we interpret the results from these experiments, I should put that caveat out there. The CONUS experiment has put a constraint on the cross section on germanium at reactors, and the Connie experiment has put a constraint on the silicon cross section also at reactors. So there are a number of open questions that the field really needs to address, probably in the next couple of years, to really make this a very fruitful enterprise. The first is that, and I want to be provocative here, but I don't want to be mean. In the case of coherent neutrino scattering, we really need to know the quenching factor accurately, as opposed to in the dark matter field, where you just need to know that it's close, right? That you need to know it close enough. I think that precision quenching factor measurements are going to become very important for experiments all experiments measuring CEvNS, but as we recently saw with the Xenon 1 ton paper, their paper was dramatically improved by the precision measurement performed by the Lux collaboration, or members of the Lux LZ collaboration on liquid xenon for the charge ionization yield. And they were able to put interesting constraints on the photon yield from just that, looking at solar boron-8 neutrinos. So quenching factors are of primary importance here if we're supposed to do real interesting physics. If you're going to be able to do, the next question is, can we even do reactor measurements? Is that even possible? I think it is. It's potentially most interesting, though, if you can deploy an ultra low threshold detector, something like Connie or some of the bolometric detectors, Ricochet, et cetera, there's a couple of that aren't bolometric that have very high thresholds that may not be able to do it at reactors, or potentially won't have that much of an interesting physics impact. But the really low threshold ones, if done simultaneously with an inverted IBD detector, an inverse beta decay experiment, may actually begin to look at the contribution to the cross section from neutrinos below the inverse beta decay threshold, where you could begin to talk about doing neutrino forensics. And that's really, really science fiction almost, but neutrino forensics at a nuclear reactor. Can you try to understand what that reactor has done? It potentially has really interesting applications with reactors that might have breeder blankets. Is it possible for us as a community to come together and set up a common theoretical framework for CEvNS predictions, incorporating all of the standard model physics, all of the nuclear effects, and all of the BSM that might arise? I think the answer is yes, and we're actually already seeing that happen as a result of things that come out of the magnificent CEvNS collaboration. I should say workshop. Is it possible that we can get we can ease people's access to other artificial neutrino sources? Certainly, Coherent did that when we all came together. We all got access to this one neutrino source, and we became one collaboration. And it's certainly possible that access to nuclear reactors for many people in larger collaborations with multiple detector technologies might actually really give a shot in the arm to the field. Neutrino flux normalizations for both spallation sources and reactors is really important, and that's something that needs to be thought about. Can we codify and make sort of normalize the use of data releases and codified data formats? We've seen hundreds of citations of our paper that people have used the data release in order to study their favorite phenomenological model that might augment the CEvNS cross-section. I think that's really important. And then as a community in general, what we're starting to do is try to come up with a prioritization of what we think the physics is going to be for the next 5, 10, and 20 years. And you sort of see some of that falling out naturally with some of the schedules that I showed earlier, based on when certain experiments will turn on. And we happen to be in a very lucky time when all of this is happening, and you have knowledge from different experimenters that are organically transferring as people go from graduate students to postdoc and postdocs to junior faculty, where they're taking their knowledge from one field to another and really making it an exciting time. So I want to end there. I want to thank everybody for their patience with me and my long-winded description of coherent neutrino scattering and my sort of selling of the CEvNS community. But I wanted to emphasize that really the community is a very strong one and actually very congenial and works together very well. And it's something that I think is actually for the benefit of the community. So I'll just leave this slide up here, and I'm happy to answer any of your questions.
Thank you very much, Phil, for the very nice talk and a lot of information.
Yes, sorry.
We will need to digest.
There's roughly twice as many slides that I didn't get a chance to tell you about because of neutrino experiments we're doing that I just can't fit in. It's a nice problem to have, but it can be very, very strange.
So are there any questions? Art, please go ahead.
Phil, great talk and well done on the work that you've been doing with Coherent. It's very valuable and very nicely done. Just looking at the prospects for monitoring reactors and so on going forward, and just focusing on the germanium detector approach, which I'm most familiar with. Where are we in terms? I mean, you described very nice germanium detectors that you're using actually at Oak Ridge to try to do this. What about the ones that are at the cutting edge of getting tens of kilovolts sensitivity stably for recoils? How close are we to that? When are we going to be able to think about deployment more broadly for things like reactor monitoring and so on?
So I think this is a very good question, and I'm gonna take the liberty to take a half step back. The ionization only detectors that have thresholds that are in the roughly few say hundreds of keV electron volt thresholds are only ever going to really be able to produce a first light measurement, and that's what CONUS has done. They really took the opportunity, took the bull by the horns, and tried to deploy it at a reactor, and they're discovering in a pioneering way a lot of the challenges that are associated with that. And I think this is a wonderful example. They're really trailblazing for people to show them how to approach background reduction, how to approach understanding the backgrounds, detector stability and thresholds, the effects of temperature. So that's wonderful. But you're right to say that really what we're after are the ones with tens of electron volt threshold.
So what was their threshold?
Their threshold, so I would say they're probably they're going to be close to 200 electron volts. They're just really touching the tail end of the highest energy neutrinos, potentially above 5 MeV. That's the sort of threshold. And so it's not to say, I mean, and that's why they deployed. They thought they were close. 15 years ago, I was trying to deploy it with a detector threshold that was 3 times higher, and we had no chance of trying to see this at the SONGS reactor. But it's really great to see that change. The really interesting thing is the tens of electron volt thresholds, and that's where you see the bolometric detectors, or potentially the ones that come from, say, super CEvNS, where you can see single electrons, or CONI, where you can see single or double electrons in these detectors. And I think we're really close. With gas detectors, you can see a handful of electrons. With the ionization only detectors, you can get really close. With the bolometric detectors, that'll be the next thing to happen. And you know, I don't want to do a prediction market here, but the stuff that I've seen come through tunnel and the calibrations that we've been able to see through tunnel and the thresholds we've been able to demonstrate for technologies, for some of which I can't actually talk about because the papers aren't out, I've been really exciting. So I would say within the next 5 years, we will see a deployment of a bolometric detector with a 10 electron volt threshold at a reactor. Whether we'll see a result or what other challenges they might run into, I don't know. But the really interesting thing there is really going after these, a simultaneous measurement with an IBD detector. If a collaboration can be developed, maybe with an existing deployment or at a facility where someone already is, where you can measure the neutrinos accurately above the IBD threshold, so that you can subtract their contribution to the recoils at the lowest energy. So all you're looking at then is the contribution from recoils for neutrinos below the IBD threshold. It's really quite interesting from an applications point of view. But again, given the challenges that CONUS has had, I don't want to predict what kind of challenges a bolometric detector will have. But I know that Julian Billard, Raymond Strauss are really having a lot of success with their detectors in Europe. And of course, and that, with the ricochet experiments and the nucleus experiments. And then, of course, Connie with the ionization only silicon detectors are having a lot of results. Minor and the super CEvNS derivative experiments are showing a lot of promise. I want to be very optimistic about that. But again, I think that the challenge will be when you deploy, what are the challenges that you see that you didn't expect? What are the unknowns?
Thank you very much for that perspective. Appreciate it.
Sorry, I was mute. I think Fabrice might have a question.
So sorry, I can't find somehow the raise hand is not showing as far as I can tell. But whatever.
Okay, sorry, I don't know. Usually,
okay. So I actually don't want to. It's a little bit the same along the same way as art. So as art waste control more generically, Phil. What I'm missing is many things, but I fail to understand exactly what the strategy is in terms of all these new detectors that are coming up. For example, Argon and Xenon have been investigating single electron detection, so relatively low threshold in the, say, 20 eV range. But what's the strategy? You have many options, I guess. Is there an overall way of defining which detector makes more sense? Or say, adjusted the Spallation lights just at Oak Ridge to keep it simple?
Oh well, at Oak Ridge, we take all comers.
Okay.
so if it's deployable and it fits, we certainly are really interested in deploying it. We have a good example would be the liquid argon experiment. The detector that was built at Fermilab originally had a 50 MeV threshold, and because of the heroic work of the folks at Indiana and in Korea, they've lowered the threshold down to 20 keV, and tens of keV is fine for the SNS, depending on what the mass is. Early on, we really were excited about the possibility of the red detector coming with 100 kilograms of xenon to the SNS, and that comes with its own particular challenges. Any detector that's slow at the SNS, on the one hand, it's really going to suffer because its background rejection is not going to be as good. So that's really the power that the SNS has, is that you have this exquisite 10 to the 4 background rejection. You don't need underground argon in a liquid argon deployment there, though it certainly will help for future experiments. But there are other surprising challenges that arise. For example, with liquid xenon, at the SNS, you have this really high flux of muons that an underground liquid xenon experiment might not normally have, a 2-phase experiment. And so when a muon travels through your detector, after about 200 microseconds or so, you're going to have an awful lot of charge creating proportional scintillation light in the gas region. And that has the potential to really wear out the photocathodes on the phototubes after a while. And so one of the things that our Russian collaborators did, they were never able to bring the liquid xenon experiment to the US because of political reasons. But one of the things they developed was a technique to gate the photocathodes after they knew a muon had passed through, so that the S2 signal could basically be shut off, or the phototubes were not sensitive to the S2 signal. So it's really about ease of use. For right now, it's like, what can we deploy that we know will work, and how many miracles do we have to perform to get it to work? And so crystal scintillators are really straightforward and easy, but they tend to have high backgrounds. Germanium detectors are really low thresholds and exquisitely energy resolution, but it's hard to get a lot of mass, and they tend to be a little bit slower. These ICPCs are about a microsecond, so they start to suffer from that. That's the strategy at the SNS. At reactors, I would say the strategy is first light. It's really important to see first light. So Connie and Konus are really pioneering that and doing a wonderful job. RED is going to begin operating this year with their liquid xenon experiment. They've, and they're going to operate at around a 2 to 3 electron threshold because of the well-known problems with single electron emission and the backgrounds that arise there, and the trapping and various things like that. So I think first light is very important, and that's what you'll see with the ionization only, the heavy targets with ionization only. But really, what you need to do to do something, to start doing physics that's going to be impactful physics beyond that's been long predicted, is going to be one of these bolometric detectors or something with a 10 eV threshold. And so that R&D has to be going at pace while we're doing that as well. So I would say that's where that program is, which is, if you can take something to the spallation neutron source, and it's fast, and it's more than 10 kilograms, and the backgrounds aren't, more than say 200 counts per kilogram day, which to this whole list right now is going to be very like, oh, that's easy, because it is not that bad. Then you should do it, and Coherent would be interested to talk to you, and potentially ESS and I think there's some stuff going on in Japan now. But the reactors are the real challenge, because there's no real good background injection. So you need to be a low background experiment where you're going to be pulsing for 18 months on and 3 months off. And so that's not very good. Your background subtraction is not going to be very good. And it really has to be exquisitely low threshold and very well characterized. That's what I would say. That's where we are in terms of the planning phases right now.
Yeah, thank you. Thank you. Great.
I don't see any other hands up, but a big appreciation about the giant miner logo in your background from Andy in the chat. So I know that you can't read when you're sharing, so that's why I'm telling you.
Yeah. So I will say that there are a few that I've missed, but in this map, I don't know if you can see the map. But because there's so many new experiments coming online every couple of months that we learn about. There's now one in Jinping, so that'll be really exciting. Or they're not Jinping; they're going to be associated with Juno, or it seems like.
Yeah.
So there's some very exciting things happening in the community right now. So it's very exciting.
So this is the last call for questions. If no other question, I would like to thank you again, Phil. Very, very nice talk. And everything will be recorded, so it's recorded, so it will be on SharePoint soon, and it will be shared to the YouTube at SnowLab. So if you want, you can get the link as well, in case you want to share it. So thank you again, and have a good week, and happy Monday.
Yes, happy Monday.
Thank you. Bye-bye.